In today's lecture, we will cover implicit differentiation and its applications. So first of all, let's start with our motivation. Why do we need implicit differentiation? Why is explicit differentiation not enough? So the curves we encounter are not necessarily functions. So let's take, for example, x squared plus y squared equals 2. So this is actually a circle centered at the origin with the radius of square root of 2. Square root of 2 minus square root of 2 minus square root of 2 over here and square root of 2 over here. So for an example, we might need to calculate the tangent to a point on this circle, the equation of the tangent line to any given point. Let's take, for example, the point 1, 1. So we know the point 1, 1 is on this circle because it satisfies the equation. If you plug in 1, 1, it gives you 2. So let's say the point is over here. 1, 1. That's my point. And the question is, find the equation of the tangent line that goes through this point and tangent to the circle or to our curve given with this equation. So basically, we are looking for this tangent line. Okay? So to find that, we need to find the slope of the tangent line. The definition of the derivative tells us the derivative, the value of the derivative at this point equals to the slope of the tangent line. So what we need is to find the value of the derivative at the given point 1, 1. However, here y is not given explicitly. That means y is not expressed in terms of x. So we don't know y as f of x. Rather, we have a closed form for y. Here, we can proceed and try to get y out of this equation in terms of x, and then take the derivative. So that's what we're going to do first. And then we will see another alternative for this. So here I can move the x squared to the other side, y squared equals 2 minus x squared, and take the square root on both sides to obtain y equals plus minus square root of 2 minus x squared. As you can see, I have two options here, plus and minus, because this is not a function. So the positive root is the function over here. Actually, this is y equals square root of 2 minus x squared. And then I have the negative root, which is this part of the circle over here. So this is y equals minus square root of 2 minus x squared. Okay? So since I'm trying to find the derivative at the point 1, 1, I'm interested only in the part above, so the positive root. So I will proceed y equals square root of 2 minus x squared. And now y is explicitly expressed in terms of x. I can easily find its derivative y prime, or dy dx, which is y prime equals the derivative of the square root, which is 1 over 2 times square root of 2 minus x squared, and using the chain rule, the derivative of the inside function, which is the derivative of 2 minus x squared, that gives us minus 2x, right? That is, we can cancel out the 2's to obtain minus x over square root of 2 minus x squared. Okay. Now, the slope of the tangent line is the value of the derivative at the given point. So let's evaluate the derivative at the given point. Y prime at 1, 1 is equals minus 1 over square root of 2 minus 1 squared, which is minus 1. So the tangent line can be then, the tangent line can be written then, because we have the slope and we know a point on this line, we can write the equation of the tangent line. Y, the point is 1, 1, so y minus 1 equals the slope times x minus 1. So this is y minus 1 equals minus x plus 1. So y equals minus x plus 2. So that's our tangent line. This one here, y equals minus x plus 2. So that means this points, the intersections with the axis are 2. So here and here. So if we ask to find the normal line, for instance, the normal line, let's recall that the slope of the normal line times the slope of the tangent line gives you minus 1. So because the normal line is perpendicular to the tangent line at the given point. So that means the normal line is actually this line over here, which is perpendicular to the tangent. So that's our normal. So similarly, to find the equation of the normal line, again, we need to find the value of the derivative, that means the slope, and then of the tangent line, this is minus 1. So that means the minus 1 over minus 1 gives you 1. That's the slope of the normal line. So again, we have the point 1, 1, and this time the slope of the normal line is 1. So y minus 1 equals the slope times x minus 1, which is y minus 1 equals x minus 1, hence y equals x. So which is the equation of the normal line here. So y equals x. Now let's see another method to solve the same problem, the so-called implicit differentiation. Implicit differentiation. So we need to use this method if we cannot express y explicitly in terms of x. So let's take again the same example, x squared plus y squared equals 2. Now here in this equation, as an equation, y is not expressed in terms of x explicitly. However, we can take the derivative of the equation. So let's take the derivative with respect to x on both sides. So that means the derivative of x squared with respect to x, which is 2 times x, times the derivative of the inside, dx over dx. Okay? Plus, then here I have y squared. However, y is a function of x. So that means, again, I need to use the chain rule. When we take the derivative with respect to x, it's 2 times y times the derivative of the inside function, which is the derivative of y with respect to x. So dy dx equals the derivative of a constant, which is 0. Here we know dx over dx is 1, and dy over dx or dy dx is y prime. And what we are looking for is the y prime. So simplifying the 2's, we have x plus y times y prime equals 0. Now we can solve for y prime, which turns out to be y prime equals minus x over y. Note that this time we end up not with only x's in the expression of y prime, but also y appears there. However, this is not a problem because we are going to plug in our point to find the we're going to plug in the point 1, 1 to find the value of the derivative, which gives us the slope. So y prime at 1, 1 is minus 1 over 1, again minus 1. So we find the same solution as over there, minus 1, and we can write either the tangent line or the normal line accordingly. Note that we can also, if we knew the expression of y, we can plug in over here to have the full expression of the y prime in terms of x. So let's take that over here. We have calculated y as square root of 2 minus x squared. So if you put it back over here, that is nothing but minus x over square root of 2 minus x squared, which is the same result as here. Now let's see another example. This time x squared plus y squared equals 4x times y. Again, here y is not expressed explicitly in terms of x. This time also y appears in a product on the right hand side. So it's even harder to let y alone on one side. For this reason, we are just going to directly use implicit differentiation. So let's take again the equation and take the derivative on both sides with respect to x. So d dx. But don't forget that y is a function of x. So whenever we are taking the derivative of y with respect to x, we have the term dy dx. So x squared, the derivative of the x squared gives us 2x plus now y squared is 2y times the derivative of the inside function, which is dy dx, equals, now on the right hand side we have a product 4x times y. We need to use the product rule. So the derivative of the first one, 4x, is 4 times the second one, which is y, plus the first one, 4x, times the derivative of the second one, which is dy dx. Note that we have dy dx on both sides, which is the same as y prime. So we need to solve for y prime, so we can move y primes to one side and everything else to the other side. So we can have 2y minus 4x times y prime equals 4y minus 2x. So now, dividing by the 2y minus 4x on both sides, we have y prime equals 4y minus 2x over 2y minus 4x. And if you want, you can cancel out the 2's to obtain 2y minus x over y minus 2x as the derivative of y with respect to x. Note that in the expression of y prime, again we have not only x but also y's. Now in this example over here, it's not possible to express y explicitly in terms of x because y appears inside the square over here and also inside the sine function over here. So we cannot express y explicitly. That means we have to use the implicit differentiation if we want to calculate dy over dx. So let's do it. Again, we're going to take the derivative on both sides of the equation. So the derivative of x squared gives us 2x plus the derivative of y squared, remember 2y times y prime, don't forget the y prime from the chain rule, equals, now we have an outside function, sine. So the derivative of sine is cosine, cosine of x times y, times the derivative of the inside from the chain rule. Note that we have a product inside, so we need to use the product rule as well. So the derivative of times the derivative of the first one is 1 times the second one, y, plus the first one, x, the derivative of the second one, which is y prime. Again, y prime appears on both sides. We have to move y primes to one side and everything else to the other side. So here we have 2y minus x times cosine of xy times y prime equals, let's move this to the other side, minus 2x plus y times cosine of x times y. Now let's divide by this one to obtain y prime as minus 2x plus y times cosine xy over 2y minus x times cosine of x times y. Implicit differentiation is not only used to find the first derivative, we can also find further derivatives, that means second derivative, third derivative, so on. So let's recall our first question, x squared plus y squared equals 2. Remember, we calculated the first derivative with respect to x as minus x over y. Now, right now, we want to calculate the second derivative, that means y double prime, which is the same as d squared y over dx squared. So that's the question. We can have two methods to find this. So the first one, we know that the second derivative is the derivative of the first derivative. So as we have calculated the first derivative, we can take the derivative again to find the second derivative. That means y double prime is the derivative of y prime. So that means d of minus x over y dx. Here we have a quotient, that means we need to use the quotient rule when taking the derivative. So I put the minus over here. The quotient rule says the derivative of the first one, which is 1 times the second one, y, minus the first one, x, times the derivative of the second one, which is y prime, over the square of the second one, y squared. It's perfectly okay to leave this in this form if you want to evaluate this derivative at a given point. For example, if you want to find the value of the second derivative at 1, 1. So we can plug in this over here. However, we need to know also the value of the y prime at the given point. So because we know the y prime, you can put it back over here to obtain minus y minus x times y prime was minus x over y. So I put it over here, minus x over y squared, which is minus y cubed times y squared plus x squared. Okay? If you also note that x squared plus y squared equals 2, you can also use this over here to obtain minus 2 over y cubed. So the value of the derivative at 1, 1 is minus 2 over 1 cubed, which is minus 2. Another method is without solving for y prime. So for the other method, we start with the equation x squared plus y squared equals 2. Now we take the derivative as usual on both sides to obtain 2x plus 2y y prime equals 0. Now, without solving for y prime, you can do it again once more. So that means here we took the derivative with respect to x once, and we can do it one more time to obtain the second derivative. Now, the derivative of 2x with respect to x is 2. Now, again, careful, we have a product over here, so we have to use the product rule plus. So the derivative of the first one, 2y. So the derivative of 2y gives us 2y prime times the second one, y prime, plus the first one, 2y, times the derivative of the second one, which is the derivative of y prime, so it's y double prime, equals the derivative of 0 is 0. Now you can cancel out the 2's to obtain 1 plus y prime square plus y times y double prime equals 0. Here you can solve for y double prime is minus 1 plus y prime squared over y. Okay? Again, you can leave it as it is, or now you can put back the y prime to see. We have the same solution. Let's plug in the value of y prime. from here to obtain 1 plus minus x over y squared over y, which is minus 1 plus x squared over y. That is nothing but minus y squared plus x squared over y cubed. Again, if you note that x squared plus y squared is 2, so you end up with the same solution as here. Today we have seen implicit differentiation and some of its applications. We have to use implicit differentiation when we cannot express y explicitly in terms of x. What's important is not to forget that y is a function of x and to include y prime in our calculations.